Hey everyone, Nitesh this side. So let's start with the question. So the question is merge k sorted list. You're given an array of k linked list and each linked list is sorted in ascending order. You have to merge all the linked lists into one sorted linked list and return it. So we can see with an example. If you can see, we have this uh, linked list, one linked list, this is second linked list and this is third linked list and I need to merge them into a one linked list which is sorted. So if you can see, this is my first. This is my second, and this is my third. Okay, so what if I take the minimum one and I insert into my output list? Okay, so I will take this one. Now I can see the smallest element is this, so I will take this. Now again I can see this is my smaller, I will take this. After this, I can see like this all element complete, so I will go to its next. I can see this third is smallest, so I will take it. Similarly, I will take this 4 and then this 4 and 5 and 6. So we need to make a one output list which need to be in ascending order. Okay. So if I go with the basic 𝗕 approach, how I will approach to this question is basically I can take create a one array. Okay. So what I will do, I will create one array and insert all this linked list into this array. So it will be like 1, 4, 5, then 1, 3, 4, then 2, 6. After that, I will sort that. So after sorting, I get a sorted array. And after this, what I can do, I can create a linked list and basically insert that into one list. So that will give me a final sorted list node. And if I calculate the time complexity for this, it will be order of n log k. Basically, n for sorting, it will cause n log n, and we have k size of list, so that's why it's log k. And for space, it will be order of n into k. Okay. So as you can see, it's taking too much time. So can we approach or can we go with a better second approach? Okay, so now let's see the second approach, how we can optimize our previous approach. Basically, if we start with every head pointer of every element, basically comparing one by one of each list node. So one will be so this will be here and okay, so now let's see the second approach. What we can do is basically we can compare one by one element of each head element. Basically, if you can see, the question is already giving us sorted linked list. So that means if we compare each head element, basically this and this with uh, each of them, if we get the smallest, we will take it. Okay, so for if we compare all these three, we get one as smallest. Okay, so we will take in our final list after, and we increment one by next pointer. Okay, one now point to this. Okay, now we need to compare this 4, this one, and 2. Okay, now if we see the shortest element, it's 1. Okay, so we will take this one into an linked list and we move forward. Now, we will again see which is lesser. So 2, 3, 4. 2 is lesser, so we will increase this pointer by 2. Okay, so we will point 2. Now, again we will see 4, 3 or 6, which is minimum. So 3 is minimum, we will take it. Now we'll increase our pointer 3 by 3 to 4. Now, again we will compare this 4 and this 6, which is minimum, 4 is minimum. Okay. So we can take any 4, right? So let's say we will take this one, this 4. Okay, we will move forward. Now we will again compare 5, 4 and 6. So we will get our final list as 4, 5 and a 6. Okay, so as you can see, we got our final sorted list. Let's calculate the time complexity for this. So if you see for time for this equal to, we are comparing with every k list. So if you can see from the start, we're comparing these three. These three is not just a k, okay? And we are doing this for all the elements. So our time complexity will be k times n, okay? And our space basically is order of n. Okay. Now, if you can see, we are doing this for all kth element. Can we optimize it? So if you can see what we are doing, basically comparing this kth list every time, like why this. Similarly, can we use some data structure which will give us the minimum element? Like we don't have to traverse over this whole kth list. Can we optimize it? So if you know for basically for optimizing or getting the minimum element, we can use something called a min-heap. Okay. Now, as already discussed, we can go with the min-heap. So what we will do, we will insert all kth head pointer to our min-heap. Okay. So our min-heap basically of type of list node. Okay. So our minimum heap will create like this. We'll insert this one into our this min-heap. Then again we encounter 1 1. So from this we will insert this one also. And after that we will insert this 2 also. Okay. So what we will do for basically creating our output list, we will take out the minimum element from the min heap. So as you can know, in min heap, the minimum element is always at the root node. So we will pop this element. So one, we will pop it and we will add it to our output list. Now we will move forward this one pointer to this. If we check, we will check, is next is not equal to null, then we move forward. So we will make pointer here and we will insert this 4 into our min heap. So now our min heap will be like, we will insert 4, but it will 𝗷𝗶𝗃 itself. So basically 1 will come at here and this 4 will come here. Okay. Now again second time we will pop this element. So this 1 will come here. Now this one here comes. So we will increase the pointer of 1 2 3. Now we'll again 𝗷𝗶𝗃 our tree. So our tree will become like this. 2 will be at top node and this will be 4 and a 3. Okay, now we can see the minimum element is now 2, so we will pop this. So whenever we removing or popping the element, we will check whether its next is not equal to null. If it is not equal to null, we will insert this into the heap, our heap. Okay, so now we will increase 2 pointer to 6. So okay, so now our heap will become 3 4 6. Okay, now we will pop the smallest element. Now 3 will come out. So this will become 3. Now our we will check is next is not equal to null. So we will move forward and insert that into our heap. So now our heap will become 4, 4, and 6. Now we will pop out the minimum element. So we will pop out this and we will insert that 4 and we will increase the pointer to 4 to 5. Now Now our heap will become, and we'll insert 5 into our heap. So heap will become 4, 5, 6. After that, we'll pop out the minimum element. So we will pop out. So this will become 4. This will be added into output list. And now our tree will be like 5 and a 6. Now we will pop out this and we will add into the list. And finally, we will pop out this also. So this will be added. So this is our sorted list. Okay, so if we calculate the time complexity for this, it will be basically order of n for all the element and for basically rebalancing or update the heap tray, it will cause us log of k because k is the maximum element that can be inserted in the heap. So as you can see, we have optimized our approach from n square to basically n log k, and space is also be optimized, it's order of k. So if you write the code for this, it will be submitted, but we can optimize this more further. So I will tell you the fourth approach which we can use to optimize this. Okay, so this will be our fourth approach, which we can use to more optimize or in lesser complexity we can do. What we can do is basically we can go with the normal merge sort. Okay. So as you know, merge sort is a divide and conquer strategy. So what we will do, we will calculate the mid and we will divide the list array into two parts. Okay. So let's say this is 0, 1, 2. Okay. We will calculate mid. So our mid will be 0 plus 2 divided by 2, which is equal to 1. Okay. So we divide our big array into two parts. Okay. So our first part will be this 1, 4, 5, and our second part will be 1, 3, 4. Okay. Now, and this is our second part also. So this will be 2, 6. Okay. Now again we will go deep dive in this. We will divide it in two parts. So basically this will be 1, 4, 5, and this will be 1, 3. So whenever we got the only one element, basically if our start equal to end, we return this list back. Okay. So this will be answer from left side, and similarly we will return this will also s equal to end. So we will return this list also. So our right result also come, and we merge the answer of both left and right. So we will use the merge function for merge sort. So our merge after this, our this list node will become 1, 1, 3, 4, 4, 5. Okay, so this will be answer coming from left. And similarly, in this case, our start equal to end. So we will return the right back to this. And we will merge the answer from left and right. Okay, so let's see the code for this. Okay, so now we will see the code with the merge sort. So what we will check first, basically we need to check if list equal to null or list dot length is equal to null. So we just return null from here, and after that we will call a partition function. Okay, so this partition function, what it will do, it will divide the array into two parts. So I will calculate left and I will calculate right. Whatever the answer coming from left and right, I will merge that. Okay, so it's pretty simple here. So I use the merge function and I just compare the value of is left value is right than right value. So I will merge that into left array, sorry, left list node. And similarly, if it is greater than right, so I will merge it into right somewhere, right list node. And if by chance, let's say the length of this, if I compare, this is 3 and this is 2. So if left is empty, basically I cross left, but right is not empty. So I just return the right from that point, and similarly for right also. So this is the basic code for this, and the you can calculate the time complexity for this is big O of n log k. Okay, and space we not taking anything, so it will be order big of 1. Hope you like this video, and I will also attach the heap solution in the description also. You can check that out. Thank you for watching my video.